Hello, class. Mr. Hasty here. Today we're going to be starting section 10, which deals with work, energy, and machines. We're going to start by defining some of our basic concepts. Work is most commonly defined as a force applied through a distance. Force applied through displacement. Now, the formula for this is work equals F times D times the cosine of theta. So, when you apply a force, the direction that you apply the force does not always equate to the distance the object moves. If you push something across a flat surface, the force and the distance would be going in the same direction, and thus the angle between the force and the distance would be 0, making the cosine of 0 1 in that case. However, if you were pushing a shopping cart, usually when a person pushes a shopping cart, they push downwards on the cart. So the angle they're applying the force at is not the angle that the cart is moving. That right there, that difference in angle, that is our theta. Now the unit for this, when you take a force which is measured in newtons times a distance typically measured in meters, we would get a Newton meter, which we are going to call a joule, abbreviation capital J. Now before I move further, you might remember that torque also was measured in Newton meters. There's a fundamental difference between torque and work in terms of their units and their purpose. Work is force applied through displacement, whereas torque is force applied at a distance. Even though they are both measured in Newton meters, they are not equivalent. Also to note is that torque is always a vector, with the direction being the rotational direction, whereas work is going to end up being a scalar, which means that it is not a vector quantity, it only has magnitude and not direction. So before we move into some examples and things, let's talk about what happens in two very specific circumstances. Number one, what happens if there are multiple forces being exerted on an object? Well, this is rather easy if you remember how to simplify net forces. You would just resolve the net force vector. So after all these are applied, maybe it ends up looking something like this. And in that case, you just use the resultant force vector. The other situation is, what if the amount of force changes over time? It's not a constant amount of force. So our assumptions in these examples are going to be the amount of force over time is constant. If the force is changing over time, you would need to find the average force exerted and use that as your force. Most often those type of problems are done with calculus, so we're going to avoid them in this discussion. So here's an example. A person exerts a 25.0 Newton force at a 25.0 degree angle downward, pushing a shopping cart a total of 8.0 meters. Determine the amount of work done. Let's do a quick sketch. So a person exerts a force of 25.0 Newton force at a 25-degree angle downward. All right, so if we're 25 degrees downward, and we're exerting a 25 Newton force, and our motion is going to be horizontal, we just have to work out the angle difference between the application force and the resulting movement. Essentially, we just need to resolve our force vector into its horizontal component would be one way to look at it. So, if we think of it like this and this are going to be parallel, meaning that we can use 25 as our angle in this situation. Oops, sorry there. So in this situation, we're just going to take 25.0 times 8.0 times the cosine of 25.0. We work that out, and we will get roughly 181.26 joules. That'd be Newton meters. However, due to sig figs, we're going to round that to 180 joules. All right. So whenever we talk about work, it involves the concepts of energy and power. So the word energy is commonly misused. Energy is defined as a system's ability to do work. Now, the relationship between work and energy is encapsulated in the work-energy theorem. Which says that work is equal to the change in energy. This means that work and energy are going to be measured in the same units. The amount of work on a system is equal to the change in energy of that system. Also, since work is a scalar, that means energy would have to be scalar as well. That also means that the unit for energy is also joules. Now, when we talk about energy, there's a lot of different types. The first one we're going to talk about is kinetic energy. Kinetic energy is the energy of motion. And a type of energy that we're going to use quite often is translational kinetic energy. which is defined as the energy due to changing position. Now the formula for translational kinetic energy, typically say Ke subscript trans is equal to 1/2 the mass of the moving object times its velocity squared. Notice, since the velocity is squared, the vector component, the positive or negative if you will be squared off, meaning that we'll get the same answer for something that is moving 5 meters per second to the right or 5 meters per second to the left. And thus, the energy does not tell us direction. Right. So before we move on to the examples, we're going to talk about power. Power is defined as the rate of change in energy. Now, the formula for power is change in energy divided by time. Now, we typically measure the time in seconds here, as we commonly do with time. And our unit for this would be joules per second, which we call watts. Now, watts are oftentimes listed in larger units such as kilowatts, and that's standard, like 1 kilowatt is 1,000 watts. And those are the equations for translational energy and power. We're now going to apply them in a couple different scenarios. So a 45.0 kilogram object is lifted straight upward a distance of 5.00 meters over the course of 8.0 seconds. Determine the amount of power required to move the object. All right, so we're looking for power, meaning that we're using this guy here. Power equals change in energy over time. Now, we currently have two methods of finding energy that have been listed. One is that the change in work, or that work is equal to the change in energy. The second being the formula for translational kinetic energy. Given the information we have a mass that's being moved upward a distance of 5.00 meters. So we can then, since it's being lifted upward, we can figure out the amount of work that's being done on that object. So we're going to instead use the formula that change in energy is equal to work. Well, then the next thing is that work is force times distance cosine theta. Now, in this situation, the force and distance are in the same direction. A 45.0 kilogram object is being lifted straight upward. So the force we're talking about is the force due to gravity. And we're moving in the exact opposite direction of gravity if it's moving straight up. So in this case, our theta would be 0, meaning that cosine theta would be 1. So we can simplify this to force times distance divided by time. Finally, we need to calculate force. And the force, as I said before, is the force due to gravity. So we can take gravity times mass times distance divided by time. Now we're in a setup where we know all the values. Gravity is 9.8 meters per second squared on Earth typically. The mass of the object is 45.0 kilograms. The distance it's being moved is 5.00 meters, and it's doing that over the course of 8.0 seconds. So we work out that multiplication and get something around the lines of 275.625 watts. But due to being restricted to two significant figures, that would mean we are going to go with 280 watts. All right, and finally, a 245 gram ball is thrown at a velocity of 26.0 meters per second. How much energy and power does it contain over the course of 0.500 seconds? So we're looking for two things here, energy and power. So in this particular case, let's start with energy. Well, we're talking about a ball being thrown. We have the mass of the ball and the velocity, and we talked about how energy for a moving object is essentially the translational kinetic energy, which is 1/2 mv squared. So in this case, we have all that information. 1/2. Our mass needs to be converted from grams to kilograms because we typically work in kilograms, 0.245, and then times 26.0 squared. Now, when we work that out, it comes out to be 82.81 joules. But due to being restricted to 3 sig figs, we're going to go with 82.8 joules. Now we can use that energy to find our power. Power is equal to change in energy over time. So what's interesting here is this almost becomes what you consider a trick question. So in this situation, is the energy changing? Nothing in this indicates that the ball is slowing as it flies through the air. So at any given point, the kinetic energy of this object is 82.8 joules. Now, if I talked about it slowing down, or if I talked about a change in energy in any way, that wouldn't happen. In this case, since there's no change in energy, we have 0 divided by 0.500, giving us 0 watts of power. All right. I will be posting practice problems to go along with this, and then solutions to those a couple days later. Thank you, guys.